So next up, we have Eric Neyman. Eric is a PhD student in theoretical computer science at Columbia University, advised by Tim Roughgarden. He earned a BA in math from Princeton. His research focuses on designing mechanisms for the elicitation and aggregation of forecasts and knowledge, which I think he'll be talking to us about. So feel free to take it from here, Eric.
Hi, I'm Eric Neyman, and I'm here to talk about joint work with Tim Roughgarden on a connection we found between the questions of forecast aggregation and forecast elicitation. So I'll start by telling you a little bit about these two questions, and then I will share with you our main definition connecting them, which we called quasi-arithmetic pooling. And then I'll give you a few reasons to believe that this notion that we've come up with is a pretty fundamental one. So I'll start by talking about forecast aggregation. So let's say that you're a meteorologist and there's a hurricane approaching Florida. And Florida's governor wants to know the probability that the hurricane will directly impact Miami. And so you, as the meteorologist, consult three weather models that tell you, one says there's a 10% chance, another says 25%, another says 70%. And you want to somehow aggregate these into one number. So what should you do? That's the question of forecast aggregation. And so the simplest thing that you could possibly try to do is to just take the average, and that's called linear pooling. And another common method is to take the geometric mean of the odds. So for example, you turn the 10% into 1 to 9, and so on, and then you take the geometric mean of those and convert it back to a probability. This is called logarithmic pooling. And it shouldn't be obvious why this is a natural thing to do, but it really is. There's a really nice interpretation in terms of averaging Bayesian evidence. And empirically, it does quite well, often better than linear pooling. So these are the two most well-studied pooling methods, and I just want to note that they work just as well for aggregating probability distributions over more than just two outcomes. So that was aggregation. Now let me talk briefly about elicitation. So this is the question of if you want to elicit a probability from an expert, how do you do so in a way that incentivizes them to tell you the truth? So this is normally done with proper scoring rules. So a scoring rule is a contract function between an elicitor and an expert that takes as input the expert's probability distribution P and the eventual outcome J, and outputs a score or reward for the expert. And a scoring rule is proper if the expert maximizes their expected reward by reporting truthfully. So the two most commonly used proper scoring rules are the quadratic and logarithmic scoring rules. I won't go into the intuition for why they are proper, but I've put the equations up here on the slide. So our contribution was relating these two problems. If you want to focus on one slide to get an overall takeaway, this is the slide for you. So the key takeaway is that there is a close connection between proper scoring rules and opinion pooling methods. And the connection is mediated by a correspondence that we found from proper scoring rules to pooling methods. So specifically, we define a notion of pooling with respect to a proper scoring rule. And we called this quasi-arithmetic pooling, or QA pooling for short. So let me tell you a few facts about QA pooling. So first, QA pooling with respect to the quadratic scoring rule is linear pooling. And QA pooling with respect to the logarithmic scoring rule is logarithmic pooling. And there are several nice interpretations of QA pooling, one in terms of maximizing the aggregator's worst case profit, and another in terms of minimizing Bregman divergence. And also, the class of all QA pooling methods are characterized by a natural list of axioms. So I really want to tell you what this definition is. But first, I want to motivate it by talking a little bit about how to choose a scoring rule. So there are infinitely many proper scoring rules. How do you choose one? And specifically, let's say that you want to decide whether to use the quadratic or logarithmic scoring rule. So intuitively, they feel pretty different. So for instance, the log scoring rule goes off to negative infinity, as you see here on the left. And one way to formalize this distinction is to think about how much the expert cares which outcome happens as a function of the probability that they report. And that is this plot on the right here. So for example, if an expert is being rewarded with the logarithmic scoring rule, and they say 99.99%, then they really want the yes outcome to happen. So much more so than for the quadratic scoring rule. And so one interpretation of this is that by choosing the logarithmic scoring rule, the elicitor is making a subjective value judgment that probabilities close to 0 and 1 are, in some sense, extreme. So let me formalize this a bit. And to do so, I want to define this function capital G. So given a proper scoring rule S, capital G is the expected reward of a truthful expert who believes P. So for example, in the case of just two outcomes, yes and no, I have drawn the function capital G for the quadratic and logarithmic scoring rules here. So the function G is always convex. And even more important than capital G for us will be its derivative, which will denote lowercase g. Or in higher dimensions, that would be the gradient. And so what little g measures is how the expected reward of a truthful expert varies locally with their belief. So little g is just the derivative of capital G. So why do we care so much about little g? So the reason is this plot at the bottom of the slide. So this is little g for the quadratic and logarithmic scoring rule. And you've seen this plot before. This is exactly the plot 2 slides ago when I talked about how much the expert cares which outcome happens. And this is exactly what little g measures. Now, this shouldn't be obvious, but it's not hard either to see that little g specifies the difference in the expert's rewards depending on which outcome happens. So the key idea behind QA pooling is that when you choose a scoring rule, you're making a value judgment about how an expert should think about various probabilities. And so if you're making that judgment, it makes sense to render the same judgment when aggregating the probabilities. So the idea of QA pooling is to mediate your pooling through the function G. So for every different function G, you should have a different pooling method. So before formally defining what QA pooling is, let me give you an example of how it works. So in this example, expert 1 reports 90% and expert 2 reports 2%. And first, we are going to do QA pooling with respect to this particular choice of little g, which is a linear function. And that is precisely the little g for the quadratic scoring rule. So here's how that works. First, you draw vertical lines from the two probabilities and see where it intersects this line. So those are the g values corresponding to the two probabilities. Then you take those values, so it looks like one of them is near -2 and the other is between 1 and 2, and you take their average. Then you draw a horizontal line to see where it intersects this curve G. And then you draw a vertical line to map that back to probability space. And so in this case, where you end up is 46%. And so that is the QA pool of these two forecasts with respect to the quadratic scoring rule. All right, now let's play the same game, but with this different function G. And this is precisely the G for the logarithmic scoring rule. And so what ends up happening is, again, you take the G values, you take their average, and then you map it back to probability space and you get 30%. No surprise, we got a different number because we used a different curve. And in fact, we got a smaller number, which makes sense because remember, with respect to the log scoring rule, probabilities near 0 and 1, like 2%, are pretty extreme. So it makes sense that the 2% would pull this aggregate probability down. So now I'm ready to tell you the formal definition of QA pooling. So, and this is exactly what you should be expecting given what we did on the previous slide. So the QA pool of M forecasts with respect to a proper scoring rule S works as follows. You take the G values of the forecasts, you take the average of those, and then you map it back to probability space by finding the P whose G value is equal to this average. And I just want to point out that you can also incorporate weights if you trust the expert's different amounts. So in that case, the weighted QA pool would be you take the weighted average of the G values and then you map it back to probability space. And as I mentioned earlier, the two most common proper scoring rules correspond to the two most common forecast pooling methods. The quadratic rule corresponds to linear pooling. The logarithmic pool corresponds to logarithmic pooling. So this should sort of pique your interest. And so now what I want to argue is, in fact, QA pooling is a pretty fundamental notion. And I'll start out this argument by giving you two alternative interpretations of QA pooling. So the first one is in terms of Max-Min optimality. So let's say that you are asked for a forecast and you will be paid according to the scoring rule S. Now you happen to not know anything about the topic. So instead what you do is you subcontract M experts. And maybe you trust the experts different amounts, so you give each expert a weight. And what you're going to do is you're going to reward the experts with that same scoring rule S proportional to their weight. Now your goal is to turn a profit. So formally what you want to maximize is your worst case profit, which is the worst case value over the outcome J of the score you receive minus how much you pay out to the experts. And it turns out that QA pooling is precisely what accomplishes this. And in fact, your profit, if you do QA pooling, is going to be the same no matter the outcome. And an alternative interpretation of this fact is that QA pooling improves upon choosing a random expert by the most amount in the worst case. So now I'm going to tell you the second interpretation of QA pooling, and this involves Bregman divergence. So let me tell you what Bregman divergence is. So let's say that you have a convex function capital G, and you should be thinking back to the expected reward function capital G that I mentioned earlier, the expected reward with respect to a proper scoring rule. So if you have 2 points, X and Y, two values, then the Bregman divergence with respect to G from X to Y is as follows. So you draw a tangent line to capital G at Y, and you see how far below X that line passes. So for example, at the bottom right corner, that is the Bregman divergence with respect to this green function G from 0.7 to 0.4. And there's a nice scoring rule interpretation of Bregman divergence, which is how much an expert loses out on an expectation if they say Y and the right answer is X. So given some forecasts that you want to pool, it is very natural to ask which forecast minimizes the Bregman divergence to all of the experts' forecasts. And this is precisely accomplished by QA pooling. So specifically, QA pooling minimizes the weighted average Bregman divergence from the pooled forecast to each of the expert forecasts. And the plain English interpretation of this is that the QA pool of forecasts is precisely the probability distribution with the property that if it is the correct answer, then the experts are least sad having said what they said instead of saying the correct answer. Now, the third reason that I think QA pooling is pretty fundamental is this axiomatization result. So so what does that mean? So it is natural to ask, so there's a scoring rule. For every scoring rule, there is a different QA pooling operator. And it's natural to ask, what is this class of all QA pooling operators? What does it look like? And it turns out that a pooling operator is a QA pooling operator with respect to some proper scoring rule, if and only if it satisfies a list of pretty natural axioms. And this builds on work by Kolmogorov and Nagumo on quasi-arithmetic means, hence the name quasi-arithmetic pooling. And I won't go through these axioms. Feel free to ask me about them at the poster session, but I think they're all quite natural. Right, so I hopefully convinced you that QA pooling is fundamental, or at least quite natural. So then where do we go from here? What new vistas does this open up for us now that we have this definition? And a really natural question to ask is about no regret learning of expert weights. So, here's the setting. You receive expert opinions for T time steps, and you want to QA pool them, but you're free to choose weights. So at each time step, you choose weights, and your goal is to maximize your score. And so the interesting thing is that if you use an algorithm such as online gradient descent, then you'll end up choosing weights in a way such that your score will be almost as large as if you had chosen the best weight vector in hindsight. So this is a pretty strong guarantee, right? I'm not saying compared to the best expert in hindsight. I'm saying the best possible weighted average, weighted QA pool of the experts in hindsight. And this falls out of a neat mathematical property of QA pooling, which is that your score when you're QA pooling is a convex function of the expert weights. So I've hopefully convinced you that QA pooling is both fundamental and mathematically interesting. And so it's natural to ask, what other questions are there, can you ask about QA pooling? And so I've put some future directions up on this slide. And meanwhile, in the minute and a half I have left, I am happy to take any questions. Thanks.
Awesome. Thanks, Eric.
Cool.
I think there are already some questions in the chat.
All right.
Okay.
Aren't typical hurricane path models determined? I don't think that's true. So there are ensemble models, like what a model has like many sort of, there's randomness. They're not deterministic. Right. Min-max formulation, does that work when the weights don't sum to 1? Right. So if they don't sum to 1, then instead of being paid the scoring rule, you're paid the scoring rule times the sum of the weights, and then it still works. How does it connect to arbitrage? Right, okay. So if there are several experts, then they might collude, right? They might decide that they want to report the same number. Basically an alternative formulation of what I've said about Max-Min optimality is that if they report the QA pool instead of their individual forecasts, then they increase their total reward, no matter which outcome ends up happening. And so then they can redistribute the surplus among them. And there's been a line of work on that.
Okay, next question. Are these interpretations only hold for QA pooling? For example, if pooling is linear but scoring rule is log, do any of these properties hold?
Yeah, okay. So if in the specific case that you just said, if pooling is linear, then scoring rule is log, then, so I mentioned the concavity property of weights with respect to, of your score with respect to weights. That holds in that particular example, but not generally. So yeah, most of these results hold very specifically in the case that you are QA pooling with respect to the particular score rule. QA pooling will never extremize. Yes, so when I talked about the axiomatization, that is one of the axioms. And I agree that there are other interpretations of what it means to aggregate scoring rules where you would want to extremize. And basically that is not a, that is not the sort of aggregation that we are looking at in this work.
Grant asks, in one of the talks yesterday, they talked about correlation between agents. Can this be extended to those cases?
So when I typically think of correlation, I think of a sort of Bayesian setting where there's some sort of maybe information structure over the possible worlds and the experts' beliefs are correlated. This is not really a work in a Bayesian setting. This is by its nature sort of axiomatic. We're working with like, this optimizes something. So there might be connections to the Bayesian setting. Right, that is one of the directions for future work, but I haven't found any connections yet. So, yeah.
Okay, we should wrap up, but there are some more interesting questions. Tobias says, the Max-Min interpretation reminds me of quasi-convexity of scoring rules. Have you thought about this connection?
Let's talk during the poster session. I'm not sure what quasi-convexity means.
Okay, and then finally, Phil points out that if all experts say 0.7 but are using different information, then you probably would want the combined value to be greater than 0.7.
Yeah, so that is a challenge when you want to extend the work that we're doing to a Bayesian setting. And yeah, I think it would be quite interesting to see if there are applications there.
Awesome. Thanks again, Eric.
Yep.